was looking at hybridization theory. So we actually went through a couple things. So the first thing we did was looking at our atomic versus our molecular. And we looked at our hydrogen atom. It would have been nice if everything was already drawn. A hydrogen atom has an s orbital. So we've got those two s orbitals. All orbitals, all electron motion moves in waves. So there is a positive aspect to our wave and a negative aspect to it. So for these two orbitals, there's two possibilities. Right? Each of these has these two possibilities. They're either both positive, or they can either be positive, go away, positive or negative, which just happens to be the signs that we've associated with these waves. Right? If we look at these two orbitals where they overlap with the same type of wave pattern, be it positive, positive, or negative, negative, they get constructive interference. And so what ends up happening is the distance, if we look at our nuclei, we end up seeing a lot more electron density in between the nuclei. And that's usually drawn by putting the nuclei on the far extremes, and we've got this area in between with lots of electron density. All we're saying by that is that they added constructively to each other. So that when we brought those two structures near each other, we've got that kind of Venn diagram issue where they overlap in a constructive fashion in between them. That constructive fashion increases the amount of electron density in between the atoms. That's it. Right? But what happens if, when they went through an overlap, that it was either positive, negative, or negative, positive? Well, now their waves are misaligned or oppositely aligned, and we get deconstructive interference. And now what ends up happening is that when we look at our nucleus again, or our nuclei again, our electron density is now pushed to the outside. There is no electron density in between them. Well, no electron density means there's not a bond. Right, well, when does this happen? When do we have this kind of appearing to be bonding situation and an appearance of a not bonding situation? Well, this happens every time we bring two orbitals near each other. Every time. Does not matter what type of orbital. Okay? We will get a bonding interaction where those clouds interact in a favorable fashion, constructive, and give us more electron density between the atoms. Or we end up with, the situation where there is no electron density between the atoms. If we have no electron density, it's referred to as a node. Right? Just an extra term. All that ultimately means is there's no electron density there. So if our node falls through the middle of our atoms, we don't have a bond. And we can take this a step further. We can then label each of these types of interactions. They're typically referred to as a sigma interaction, which we almost always abbreviate as the Greek letter. Okay. In that bottom situation, we have a sigma bonding interaction. Well, that's good, so we don't put any caveats or stars or anything next to it. We just say, hey, that's good, we got a sigma bond. But in the upper situation, that condition is the same type of thing. We're attempting to do a direct overlap. And once we've done that direct overlap, we had that deconstructive interference, which prevented electron density between the atoms. Okay, so we have the same type of overlap. It's still a direct overlap, so it's still a sigma type interaction. However, we want to clarify that away from our other interaction. Okay, in the bottom one, it was constructive. It was a good thing. And the top one, it's a bad thing. So we can typically refer to that as a sigma anti-bond. Why anti? Because it's fancier than not a bond. That's all we're trying to say. And that symbol becomes sigma star. So the sigma is in reference to the direct overlap of two orbitals. What do those orbitals have to be? Any orbital. Right? As long as we get a direct overlap of any two orbitals, we end up with this sigma type bond and anti-bond. And remember, we can't create or destroy matter. So if I start with two atomic orbitals, how many molecular orbitals do I need? Two. Every single time. If I start with 4 atomic orbitals, how many molecular orbitals do I need? 4. Every single time. Right? what those orbitals are is then going to break down into this either bonding or anti-bonding. So if I brought in 4 total atomic orbitals, right, well, it splits evenly between the bonding and the anti-bonding. So how many bonding orbitals would there be? 2. How many anti-bonding? 2. The molecular orbital diagram says nothing about if a bond is valid or not. All we're trying to do is say, where do the electrons exist? Period. These are the possible states for that electron to exist. So if we looked at hydrogen, okay, or the H2, let's ignore all of this anti-bond stuff, or sorry, the atomic system. What we now have is this molecular drawing. And we want to decide if we have a bond or not. Well, to decide that, we have to know if there's electrons. If there's no electrons, it doesn't matter what our possible states are. If there's nothing there, we can't have a bond. Okay? So what would we do? We'd look back to the molecule we were trying to draw. We were trying to draw H2. We then have to decide how many electrons are present. How many electrons are present in H2? 2 electrons. I now take those 2 electrons, and just like we did for atomic orbitals, we now can put them into our molecular orbitals. So how many electrons can fit in an orbital? 2. So I take those 2 electrons and I put them where?
The lowest energy state.
Lowest energy is the best answer for this. We want to put them at the absolute lowest energy. Well, which is the lowest energy? Bottom one. Okay, now we decide, do we have a bond or not? Well, where are our electrons located? In the bonding system or the anti-bonding molecular? Bonding. Do we have a bond? There it is. That's it. Okay. How do we predict if there's not a bond? Well, we could start to add more electrons in and see what's happening with those circumstances. If you would like to play with that, by all means, you are welcome to, but completely unnecessary. Right? Because organic chemistry is not about looking so much at the anti-bonds as it is looking at the bonds. Okay? So don't stress too much about the anti-bonds, at least not yet. Okay? Hybridization theory is now a more advanced application of this, but it's ultimately the same idea. I take that s orbital, which is a nice sphere, and I take a look at my p orbital, which overlays over the top of it. Well, my p orbital already starts with a node in it. All my p orbitals start with that node. Okay, so what happens at the node? We have to switch the sine wave, okay, or switch our positive versus negative, which is why when we look at a p orbital, you'll see one side shaded and one side not. Why do we not do that with an s orbital? It's sphere. There is no node within it. It's all the same shading. So if we now look at the overlap of a p orbital with our s orbital, do we see the potential for some constructive or deconstructive interference? Yeah. So what ends up happening with that system is we've got our nucleus. On the far right, we have deconstructive interference, which means our electron density doesn't exist out there. Okay, so we get a relatively small amount of electron density on one side of our lobe. On the other side, what happened? We get a lot of electron density. Okay, and yeah, this weird shading in shape looks kind of goofy, but that's kind of what's happening. We're looking at how these things can add and subtract. And what we push to as far as representing this is if we look at our nucleus again as blue, we have kind of a distorted p orbital. Well, this distorted p orbital is the combination of the s and p orbitals. And that gives us this new shape. Right, and when we look at this, it has a node running right through the nucleus. Okay, so if we had to predict, should it be higher or lower in energy than the s orbital? Higher because, one option, it's a combination of the s and the p, and our p are higher in energy than our s. Well, why are p higher in energy than the s? Single orbital can only hold 2 electrons. There's a node in the p orbitals, which means electrons can't exist there. that's naturally going to be a higher state. The more nodes we have, the higher in energy. Okay, we want our electron to have as much free motion as possible. So our p orbitals will necessarily be higher in energy than our s orbitals. Okay? The textbook has gone through, and I'm actually already sending them an email complaining about this. They've shown this description of what we'll call in general here is an sp hybrid orbital. Okay? This does not mean sp1 or sp2 or sp3. I'm just saying that I'm taking an s orbital and some number of p orbitals. I generate this relative shape. All right, that is what this sp type hybrid orbital looks like. The textbook has taken that a step further and said it's a bit tedious to draw on that stupid little ball thing that doesn't do anything. Why would it not do anything? There's no electrons. Okay? Those electrons are so close to the nucleus that if another atom tried to bond on that side, it's just not going to be able to get into it. We're going to get nuclear repulsion. So they have gone through and converted our sp orbital into something just looking like this. Okay? They're just ignoring that node. It is there. That little piece is floating out there. It just makes our drawings very, very confusing, and they're already confusing enough as it is, so we try and get rid of that node just to simplify our overall drawing. Okay? So, when we shift to hybridization theory, it's ultimately coming up with looking at our molecular structure. We've got Lewis theory, we've got Vesper theory. All of these things give us some idea of shape. Well, the shape is ultimately where electrons can exist. So we have to have some explanation of how our electrons can move around. Well, electrons are relatively confined to orbitals. So we have to have some kind of depiction for orbitals to explain those shapes. Well, the atomic orbitals do not satisfy that. We cannot use our atomic theory because the bond angles are way, way off. Okay, so that's where hybridization theory came in. And the crude method is that we just take our atomic orbitals and we pretend they're clay, we mash them all together, and we make some new orbitals that go exactly where we want them to go. Right? Well, it's actually kind of close to what's happening. Right? Involves a lot more quantum physics, but hey, pretty close. So that's where our hybridization theory is coming from. The important things that we get out of this is looking at what orbitals and the relative shapes of those orbitals, okay, relative to each other. So we end up with three primary types of hybridizations. Are there more? Think back to 151. Okay, or you can even think back to all of your shapes that you may or may not remember from 151. According to this hybridization theory, what's the most atoms that you can put around an atom, center atom? 4. I can only put 4 atoms around an sp3 center atom because there's only 4 places that I can put 2 electrons. So that would mean the biggest shape that we could possibly make would be tetrahedral. Is that true? No, we do have other shapes. How do we get to those other shapes if our hybridization theory stops at 4? You add in the d orbitals. So when can we worry about our d orbitals as far as shape goes? After our third energy level, because at the third energy level, that's where d orbitals come into existence. So we could go through a whole other argument of d orbitals and geometries and all those fun things come out of it, but we don't worry about that in organic chemistry because it's too hard for us. We focus in at that second row. All we care about carbon, nitrogen, and oxygen. Right, so we keep it as simple as possible. We kind of ignore those other aspects, so we don't need to stress about those. When we start at our fully hybridized state, we'll refer to it as sp3. There are 4 hybrid orbitals that come out of that because I put in 4 atomic orbitals. The name that we unfortunately gave to it was sp3. sp3 refers to all 4 of those types of orbitals. Okay, so it's just another name given to it. Okay? All 4 of those orbitals need to be equal energy because that's how we get the tetrahedral shape. When we move to sp2, we end up with 3 hybrid orbitals. Okay, well, to get 3 hybrid orbitals, we take the s and 2 p orbitals. Well, we can't create or destroy matter, so what happened to that last p orbital? Unhybridized, it's still just chilling there. Okay, waiting for something to do. We'll look at what it does in a little bit. What happens when we move to sp? Well, we take the s and 1 p orbital, and we can get 2 hybrid orbitals. And we get 2 p orbitals left over. So our s-type orbitals are what are allowing us to form our sigma bonds, okay, where we get a direct overlap along a bonding axis. Okay, so if you see sp anything, the type of bond generated by that type of orbital is sigma, always. Because we're now putting electron density directly on a bonding axis that's going to result in direct overlap of those orbitals. So if I take an sp hybrid orbital and I overlap it with an s orbital, how many bonding orbitals are made? Draw in our lower left-hand corner. We're taking an sp hybrid orbital. There's that stupid little node. There's that guy. Here's our s orbital. I definitely don't have the space. Well, actually I do. I'll squeeze it in there. And I look at the overlap of these two. I bring them in close enough to each other where they can start to interact. How many bonding orbitals are made? Let me switch the question. How many molecular orbitals are made? Let's bring those in close enough to what happens. Those two parts of the circles overlap. If they're equally shaded, what happens? We get constructive interference, right? If they equally overlap. That constructive interference means what happens to the electron density? It increases. Where? In the overlap, which is located between our nuclei. So if we looked at our drawing down below, we'd have that stupid little node that didn't do anything, and then we have more electron density now in between. But what if they didn't overlap nicely, or one was positive and one was negative? What's that? What kind of interference would you get? Deconstructive interference. And what happens? There's now very little electron density between the atoms. How many molecular orbitals are generated? Two. The molecular. Why not? Our molecular orbitals are where we're looking at those two nuclei now interacting with each other. We've got one at the bottom, and we have one interaction up top. We didn't ask anything about nodes. Okay, so it's not how many blobs there are there, it's how many groups of blobs. So we've got 2 molecular orbitals. Interesting, I take 2 atomic orbitals, even though they're different, and I make 2 molecular orbitals. Okay, which is what we just said. You take any orbitals, mix them together, you generate 2. Okay, or you'll generate the same amount. That bottom one, what do we want to call that one? Now that we got that direct overlap of electron density. Let's avoid naming our molecular orbitals. But interesting point. Well, I don't want to go through and label this as S2P because when we looked at our hybridization, that was ultimately to determine, believe it or not, our atomic orbitals. So that was a bad phrasing up there. But it's our new atomic orbitals that allow for molecules. Okay. So what do we reference two orbitals in a molecule where they have direct overlap? What do we call that? Sigma bond. We have a sigma bond. What's the top circumstance? Antibond, or sigma star. Exactly the same as with our hydrogen atom. The only thing that's different is that instead of using two nice spheres, we're using this weird dumbbell shape. Why do we have to use the weird dumbbell shape? Because that helps us understand the bond arrangement, okay, or our geometry around that atom. Kind of, sort of. So, number of orbitals in our hybrid will equal our number of sigma bonds. So if you take a look at an atom that is sp3 hybridized, that generates how many orbitals? 4. How many sigma bonds are you going to get, potentially? 4. Okay, so we can use that as reverse logic as well. If we see 4 sigma bonds, what type of hybridization do we need? sp3. If I see 2 sigma bonds, what type of hybridization do I need? Just sp. Okay. So I don't quite want to look at our BH3, but let's jump to our CO2. So if we drew out the structure of CO2. In theory, you all can jump to that one pretty quickly. And really what we're going to be concerned about is what's happening on that carbon. Okay, and we'll also look at the oxygen a little bit too. But how many groups of electrons are around that carbon? Or let's actually switch it up. How many sigma bonds? Only 2. That's a little bit weird because there's 4 lines there. Okay, but our sigma bond is only a direct overlap. So we're going to end up with sp sp hybridization, which then means if we went to look up at our hybrid atomic for our carbon, we'd have 2 sp hybridized orbitals, and we'd end up with, I kind of drew that a little bit off, 2 p orbitals left over. Okay. What happens with our oxygen? I'm going to condense that a little bit. What hybridization do we expect for our oxygen? Our oxygen ends up being sp2. So there's one kind of caveat issue that happened with that last rule summary that got posted up there on that previous slide. Number of sigma bonds. Well, in this case, oxygen has how many sigma bonds? Only 1, but we end up having to treat it not as sigma bonds, but as groups of electrons. We really have 3 groups of electrons around that oxygen, which means its hybridization is sp2. So if we went through to try and draw its diagram, we'd end up with our 3 hybrids, and we'd have what left over? We'd have a p orbital left over. Okay? And if we now want to evaluate how this could work, or what's going to end up happening with this, okay, well, the ones off axis, what's going to be sitting in these off axis orbitals? It's really going to be our lone pairs. Okay, those are going to be the groups of electrons in our hybrid orbital. But what's left over? What's the other one going to do? It can overlap with the carbon. So if I look at the sigma bond my carbon is contributing an sp orbital, and my oxygen is contributing an sp2. I have a direct overlap of those two orbitals. That direct overlap is going to generate this sigma bond. How many electrons can I make or put into that new molecular orbital? 2 electrons. So if I look at the bonding here, I expect 2 electrons to go into this. What do 2 lines mean? 4 electrons. We got a problem. Right? Our electrons don't stack up right. What's happening? Where are those other 2 electrons? Isn't there another bond or another molecular orbital there? Say the sigma star. Couldn't I put 2 electrons into that? Why no? It's pretty darn high in energy. If I did put those 2 electrons in there, what's the net result? No bond. That's a bit problematic. All right, so there has to be somewhere else to put those electrons. Where's that somewhere else? We have 2 orbitals left over. I'm going to call that py and pz. Right? It doesn't really matter what our p orbital is on the oxygen, but let's go ahead and call it y. Okay, so what happens here is I now have these 2 orbitals, okay, straight up and down. Pens. Give me pens. We'll assume that's our relative shape, 2 vertical pens, okay, for our p orbitals. Right? And if we looked at our sigma bond overlap, as we bring these 2 atoms near each other, we're probably going to hit overlap there. Right? We'll do the p orbitals overlap each other then. So for overlap, that means there. Now we have overlap. Would we have overlap between our p orbitals? No. There is no direct overlap between those p orbitals. However, what is special about electrons? They can jump. So as long as they jump from one pool in one phase to the other pool being in the exact same phase, they're happy. But what happens if I now turn one of those atoms? There's now no pool to jump into. We look at that top part. There's nothing there. Okay, so what has to happen? I must make sure that I'm in that perfect alignment so that my electrons can jump. This is why it doesn't matter which p orbital I use, because what's going to end up happening? If I said pick the pz, what happens? The structure says this sucks and rotates. And I'm now aligned into that perfect setup where the electron can now jump. It has more space to move in. What we've now done is done an indirect overlap. I should probably not use a marker on the iPad. And we've got our carbon p orbital and our oxygen p orbital. With those in the same phase, the electrons, dang it, I need to give more space. The electrons can now jump back and forth. Well, if they're aligned in the same phase, what ends up happening? There's our purple nucleus in both of those. I get electron density located between the atoms, okay, sandwiching around it. I now have electron density between the atoms, which ultimately means bond. What if they were out of phase? I end up with no bond. Now the electron density pushes away from the center of the atoms. And I can't cause the electrons to jump back and forth. This brings up an interesting dilemma. That dilemma being we don't have this direct overlap anymore. So if we're going to go through and try and label what type of interaction we've got here, we cannot call it a sigma bond. Because the sigma bond was in reference to the direct overlap of orbitals. There is no direct overlap of orbitals. Okay, so in this situation, we have an indirect overlap. So what do we call it? being the creative people that we are. We call it an indirect sigma bond, nice. Okay. We reference it as a pi bond. It's a bit weird. Why did we come up with pi? Well, what did we call the other one? Sigma. What was the first orbital used in making a sigma bond? S. Oh, that's funny. S and sigma begin with the same letters. What's the first letter of our orbitals being used to make this indirect overlap? P orbitals. With the indirect overlap, we have p orbitals involved. We are looking at a pi bond. But what happens if they don't overlap? We have an anti-pi bond, usually said pi antibond or pi star. Okay? Same deal. We started with 2, we end with 2. One's bonding, one's anti-bonding. Every time. Okay? The reason why this theory becomes helpful is now how many electrons can exist between our 2 atoms of carbon and oxygen. I have a sigma overlap and I have a pi overlap. And those electrons are not existing in the same space, which is important because we can only fit 2 electrons in the exact same space. All right, so what does that end up meaning? Well, I've got a sigma bond and a pi bond. Well, the sigma bond can hold 2 electrons. The pi bond can hold 2 electrons. How many electrons are now between my atoms? 4, which is exactly what we predicted from our Lewis structures. So while Lewis structure may have had some flaws, he was still able to predict how many electrons were supposed to be existing in that space, okay? Even without having a complex understanding of molecular orbitals. Okay? So now when we look at a situation where we have a multiple bond, what we're looking at is the existence of a sigma bond, because all sigma bonds, or all first bonds, will be sigma. But if I want to put more electrons there, put in a stronger bond or a different bond, I have to put those electrons into a different orbital overlap. That different orbital overlap is a pi bond. So a double bond is now the combination of a sigma bond and a pi bond. I have 2 bonds, which gives me double. How do I get a triple bond? So let me erase all of I sure hope you were okay with me erasing all of that. I didn't like the oh my god response. That's not a good thing. So we can look at our sigma bond happening in between. So we've got our red for our sigma. We've got a pi bond happening on the outside. That gets us a double bond. Okay, well, I've got electrons between the atoms, immediately between them, and I've also got them on the outside. How can I possibly get another pair of electrons in there?
If you have another pair.
Where do I put that other pair? This is really hard to draw. We can put it on the axis. I'm going to shade the back of this p orbital. Can I get a 4th bond? That sounded kind of preachy. Can I put a 4th bond in here? I have completely surrounded that axis with electrons. There is no other place to put electrons. Okay? So theoretically, our answer would be no. How many of you have seen 4 bonds around an axis? Good, I haven't either. According to this theory, we shouldn't have them. Kind of cool. Okay? So, what you need to be able to do is being able to look at an individual structure, or a formula, get to the Lewis structure. Once you've got the Lewis structure, then come up with a hybridization. So it doesn't matter what it is. Okay? You need to be able to give me that hybridization information. And that's because there's certain key aspects that fall out of this theory. So let's back away from the purple. Okay, let's envision now if we turn this molecule, which I may have to do with pens. Yeah, let's go ahead and do that. color code this because we did the red. So here's our red with our sigma bonds. There's our bond. Nice and tight, got a bond. Direct overlap. That's why they connect to each other, right? Okay. What happens if I rotate? Does that bond break? No. Overlap stays constant. What does that mean is an interesting feature of sigma bonds? They can rotate. Why does that become a problem? Well, if I asked you all to draw me right now, please don't, because I don't want to see those later. Okay? But if I asked you to draw me right now, you might be able to come up with a rough approximation of what I look like, at least close enough. But if I now turn around and I ask you to draw me again, you're going to draw the exact same thing.
No.
Interesting, why not? Still the same person. Still the same person.
Looking at it from a different angle.
Looking at it from a different angle. But now all of a sudden when we look at a drawing for an organic structure, we go, oh, well, it's drawn entirely different. It must be a different thing. All of our structures are freely spinning, rotating in a solution, which means any particular angle can generate a structure that looks dramatically different but is identical, just like me just turning my back. Okay? What makes it even worse? If you drew me like this, you say, okay, that's a reasonable drawing. What if I did this? Your drawing now looks different. But am I still the same person? Am I still the same molecule? Yes. So our sigma bonds become problematic because that rotation can further complicate our drawings. We can take something we're just looking at it just straight on, and now rotate, all of a sudden it doesn't look the same. But it is. And it isn't. We'll get into that too. Right, what happens with a p orbital? Now with our blue pens. What we said is our s orbitals directly overlap and cause the bonds, or cause that bond length to stop. Okay, so our p orbitals never directly overlap. Okay, but our electrons can jump back and forth as long as they're in the proper phase. What happens if I rotate? We change our view on the molecule when we do that rotation. There's now no overlap. What does that mean? Broke the bond. We can't break those bonds easily. Because the atom is, no, I want that bond. I want the electrons to be able to move over a larger area because that's more stable. Right? So our p orbitals, if we see a pi bond, what that ends up meaning for us is that that bond cannot rotate. It is now locked in that particular conformation. Regardless of what that conformation is, it cannot change. Okay? That's a pretty massive conclusion to be making, all based off of our molecular orbital theory, okay? And recognizing that hybridization. So, if we tried this around with a slightly more complex structure, we could look at the orbital overlap, or our orbital composition for ethane, C2H4. We could look at the Lewis structure, the electron groups, the hybridization, and evaluate all of the overlaps. And your textbook does a really nice job of drawing all of this. There's a couple things that become interesting within this. If we drew out our Lewis structure, hopefully you would all come to the conclusion that's very similar to what they have drawn there. Probably come up with something like this. Or, just to throw it out there, you might have come up with something like this. So let's take a look at those two bottom drawings. Which is more correct? Why the left? And good. Bond angles. When we draw our structures, we're trying to, as accurately as possible, reflect the three-dimensional structure. Well, the electron groups around each of those carbons is 3, which gives us trigonal planar geometry, which means I should show bond angles with 120 degrees. The structure on the right will still get you credit 9 times out of 10. But if something comes out of the particular geometry, you won't be able to answer the question as accurately or as easily with the structure on the right. So try to draw your bond angles appropriately. Which brings up another issue. If we look at the structure as we would draw it from our Lewis with the proper bond angle, how many wedges and dashes are there? None. Why? What's the geometry of each of those carbons? Trigonal what? Planar. Do I need to show wedges and dashes? No, there's absolutely no reason to, because where's the plane? The plane of the paper. I don't need to show wedges and dashes. Completely irrelevant to adding those. But then that brings up the next question. Why on earth did they show them? Why are they showing a different view? What do they do with that new view? Draw the hybridization. And in particular, there's one particular hybridization that is of critical importance to how they drew it. The p orbitals. Where are the p orbitals? They are always perpendicular to the plane of your bonding axis. So if we look at the p orbitals on the drawing that we've got down at the bottom, I'm going to add my little shading there so you can see that there's one behind it. That looks really obvious. Yeah, thank you, Mike, for showing us the p orbitals. Okay? But if I take that structure and I grab those hydrogens and I pull them up and towards you, okay? Yeah, the hydrogens that I grabbed at the bottom are now coming at you. What happens to the other hydrogens? They're going away. So now when we go back and look at their drawing, what have they done? That's exactly what they did. They took the two hydrogens at the bottom and they just pulled them out at you. Okay? But because the structure must remain planar at all times, then now the plane for this molecule is perpendicular to our paper. So we have to show wedges and dashes. Why did they bother to go through and do that? Wedges and dashes are a pain. I don't want to have to draw those. They did that because what happens to the p orbitals? They're coming in and out of the board, and I now rotate the structure. I can now see them. So depending on what I'm looking at, I may draw the structure slightly differently, okay, depending on what I want to see. So in this case, if I do that rotation, I can now see that those p orbitals overlap. Why does that become important to me? Well, now I know I have a pi bond. What's special about a pi bond? I can't rotate. Okay? So, here's a new structure. Let's step back, actually. If I rotated, would that change my compound? No, they're all hydrogens all the way around. So if I rotate it, if I can't tell the difference between a hydrogen, which I can't, looks like the exact same. But what happens if I change my structure? We've got these two compounds now. What's the relationship between those two compounds? Don't look at the bottom. Here's the curtain. Don't look at the curtain behind the curtain. What happened to interconvert between those? So what am I asking you to do in this case? What I'm asking you to do is look for a difference. It's up to you. Some people can see the difference right away. If you can't see the difference, look for the similarities and stop looking at that. Okay, so our similarities. The R is down there. Hydrogen's up, hydrogen's up. Where's my difference? The orientation, we don't want to address the sigma bond on the left-hand side of that structure. The R group is aimed down, the other R group is aimed up. How could I possibly change my compound? Or what could I possibly do to get that to happen? What would I have to do? Rotate. If it was just a sigma bond, could I do that? Yeah. Is it just a sigma bond? No, that second line now says that there's a pi bond, which means, can I do that rotation? No. All right, well, then that addresses the next issue, or it gets to the next issue. Are these structures different? Is there any way I can spin, flip, or rotate the structure, not the bond, but the structure, so that they directly overlap? There is no possible way to do it. So I have to come up with some way to name these structures so that I know that they are different from each other. That difference is what's referred to as cis-trans isomerism. Okay? Because everything else is connected exactly the same. The only difference is the orientation of those groups around the double bond. All right? How do we go through and label that or determine that? Well, see what happens if you do that rotation. If that rotation changes your interpretation of the structure, then yes, you have cis-trans isomerism. Right? If not, then no cis-trans isomerism. So let's take a look at the bottom examples. And yes, I'm going to give you some rules to help you get through this. But first, let's take a look at some problems. Bottom 4 structures. Any of those exhibit cis-trans isomerism. Any of those exhibit cis-trans isomerism. Do we want some rules? Yeah? All right. Let's look at some rules for determining your cis-trans isomerism. First thing I want you to do, cut pi bond in half. Anybody have a problem with that statement? You should. This is just our interpretation of it, so we are not breaking the bond. We're trying to separate the structure and simplify how we look at it. What's the issue you should have with that? We're not breaking the bond, so that's one issue. There's another issue. Which direction? Okay. There's two ways we can cut it in half. We can cut it in half along, I guess, our x-axis, or we can cut it in half along our y-axis. That makes a pretty big difference. So what we want to do is cut it in half, bring in some trigonometry or geometry words. And now I said those words, I don't know how to spell this word. Perpendicular. Close enough. Perpendicular to the bond axis. Where's the bond axis? This is our bond axis. So if we cut it in half, we're looking dot, 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 dot. So now what we've got to do is look at each half. Are there different atoms attached? Are there, let's not say different, let's say distinguishable. Or distinguishable groups. If yes, what do you think? We have cis-trans isomerism. If no, it's an if no, then no. I did not say it means cis or trans. I'm just saying, do we have it? So if we take a look at the structure on the left up top, if I look to the left side, I have H and I have R. Are those different or distinguishable? Is H different than the letter R?
Yes.
Yes, thank you. They are distinguishable. Okay? Look to the right half. I have H and I have R. Are those distinguishable? Yes. What does that mean? Cis-trans isomerism. Take a look at the bottom structures again. Try to identify. We'll start with cutting these each in half. So I cut in half perpendicular to the bond axis, and I evaluate each side. Okay. Is chlorine different from hydrogen? Yeah. Come back to that star in a second. Is carbon different from carbon? No, but can you tell a difference between those two?
Yes.
How do you tell that difference?
There's an action mechanism.
It has other things attached. So if you can't tell a difference at that very first atom, what should you do? Move to the next one. Can you still not find a difference? Move to the next one. Can you still not find a difference? Move to the next one. You continue to do that until you find a difference. What happens if you get all the way to the end? You did 20 different checks all the way down and there was no difference. Then there's no difference. That's it. Then they aren't distinguishable. Okay? Which means no cis-trans isomerism. So if we take a look at this, we go out to a carbon and to a carbon. We could then take it out and say, hey, I go out to a carbon or a carbon. Well, that's not much different. So I can go step back to my original. It goes out to hydrogen, and the other one goes out to carbon. Is there a difference? Yes. What we want to do is use those in blue. So we have differences, which means, does this structure show cis-trans isomerism? Yes. Move to the next one. Is there a difference between these two carbons? The blue ones? Yes. I'm going to star that one. Is there a difference between these two carbons? No. No difference? No cis-trans isomerism.
So both halves have to have.
Both halves. Oops. I thought I had that in there. I wrote this out earlier in the tutoring center, and I said both there. Single groups on both halves. Last one. Cut it in half. Can we tell the difference between hydrogen and hydrogen? No. No cis-trans isomerism. Let's take a look at the first one. Cut it in half. Do we have differences? Yeah. Okay, so now let's take a breakdown on whether we have these yeses and nos into what they could possibly be. We'll again shift to the second one. Okay, you'll notice that I went through and actually assigned stars. Stars go to the heaviest atom. So when we compared chlorine to hydrogen, chlorine is heavier than hydrogen. What did I compare in the second one? Carbon to hydrogen. Good call. I'm not comparing carbon to carbon because there was no difference. I'm not comparing carbon to carbon. There was no difference. What I'm comparing is carbon to hydrogen. Carbon is heavier, which means my original atom on that double bond has the higher priority. Okay, so I'll give that its star. Now we can cut parallel to the bond axis. Where are those stars located? They're on the same side of that line. If they're on the same side, they are referred to as cis. Okay. What if they'd been on opposite sides? Trans. So cis just means same side. You get lots of S's and sounds. Okay, so I didn't mean it like sounds, but it kind of came out that way. Cis means everything's on the same side. What is trans going to mean? Opposite sides. Okay, let's take a look at that first structure. Cut it parallel. Where are stars? Same side. So we would say that this is cis. We run into a slight issue with this. Can it exhibit cis-trans isomerism? Meaning, can I rotate that bond? Okay, let's say we break it, spin it, reform it. Can I do that? Why not? It is physically impossible to do that with rings that are smaller than 8 carbons. Okay, how many carbons are in this ring? 5. With only 5 carbons, that double bond cannot physically be trans. Period. Well, if it can't be trans, do we have cis-trans isomerism? No. So it's kind of a weird one because our ring will still have this appearance of cis-trans isomerism, but it can only be cis. It cannot be trans. Once we have 8 or more carbons, then it can be physically allowed. If you're having a hard time visualizing why it can't be trans, you're going to have a very hard time visualizing that. Build a model. Right? Build a model and force that bond to be trans. What you will end up noticing is that to connect the ring together, you will physically have to rotate it back into being cis. Okay? Those atoms get too far away from each other to close the ring with a 5-membered ring. It's also too far away for a 6 or a 7-membered ring. Okay? So we will only be in cis conformations for those. So if you are asked, does it have cis trans isomerism? What's the answer? The answer is actually no. Tricky. Questions? As far as going over it again, what I'll say is that rings less than 8 carbons cannot be trans. Okay? It's one of those things that's just kind of a memorization thing. You will very rarely ever see it pop up. Okay? So rarely that if you check the textbook, it may be 7. Okay? I think 7 and less cannot do trans. I'm not positive on that, though. If we push to molecular orbital diagrams, within this big picture, okay, for our C2H4, you'll notice that they've got lots of molecular orbitals, and you may wonder, where are all these things coming from? And we'll look at all the possible overlaps. There's an overlap between what atom here? Hydrogen and the hybridized carbon. So there's one bonding molecular orbital. What about the other one? There's 2, 3, 4, 5. If we have 5 bonding orbitals, what else do we have? 5 antibonding orbitals. Straight off of looking at that molecular orbital picture. What about our pi bonds? Okay, we have p orbitals here. Those p orbitals should be lined up where they overlap. Okay, that indirect overlap. If they line up where the electrons can jump, where we got equal pools, then what happens? You get a pi bond. So there's our pi bonding orbital. What if they were oriented where they were on opposite sides? You get the pi antibond. Questions on that? Because I got one if you don't. Why is the pi higher than the sigma?
Because it takes more energy to jump across.
Why?
More space between.
We could try and pull a space argument. That's not a bad one. I think there's an easier one.
Because it can't be broken as easily.
What orbitals are used to make the sigma bonds?
Oh,
The sigma bonds.
oh,
The s orbitals. What orbitals are used to make the pi bonds? P orbitals. Which is higher in energy? P orbitals. Which bond would we predict to be higher in energy? Probably the one using higher energy orbitals. Okay? That tends to make sense. It's not always true, but it's pretty darn close. Okay? What happens if we turned it into acetylene? Sorry, I see your hand. Go ahead. You can ask that.
You said that the pi bonds are higher in energy because they have the nodes.
Yes.
Why does that make them higher in energy?
You're now defining a space where electrons cannot go. Okay? So let's say we take you in this classroom. Okay? Except now I say you cannot move outside of your chair for the rest of the day. Do you get higher in energy or lower in energy?
I'm gonna get grumpy.
There it is. You're going to get pissed and want to break out. Okay? Electrons are ultimately doing the same thing. We are now confining the electron to a smaller space. You cannot move outside of this. It's got a lot of energy. It needs to release that somehow. That's how it shifts to a higher energy state. So by confining it, we actually increase its energy. Okay? So when we talk about acidity, it's the same kind of thing. The higher energy our structure, the more reactive it becomes. If we can confine electrons to a tiny space, they are very reactive. If we take those same electrons and spread them over a larger area, what happens? More dispersion, they are less reactive. Okay. I know we aren't talking about this quite, yeah, we kind of are. Actually, let's do that. If we switch to acetylene, how would our picture change? Here an add, yes?
CH3
Two more p orbitals.
I have another pi bond So I would have 2 pi bonds and 2 anti-pi bonds. What happens to my sigma bonds? I have 2 less, right? Because I don't have those extra 2 hydrogens. So I would drop down to 1, 2, 3. 3 sigma and 3 sigma. Okay? Because I lose the bonding and anti-bonding interactions of those extra hydrogens. Okay? What else changes about the carbon? Actually, let's see. Do I have a better figure for this? Don't quite have a better figure for it, but this is going to get at what you were talking about here, sort of. We looked at our Lewis structures for each of these. Super exciting to draw out all these Lewis structures, let me tell you. What types of bonds do we have? We're changing the hybridization, so we got lots of sigmas, we got some pi's popping up, but the carbons are sp3 here, they are sp2 here, and sp here. So a couple questions that could come out of this would be, what is the percent S character for the carbon atoms? It's kind of an odd question. I've never really understood why it's asked, but it does get asked. What is the percent of S character in our carbons in this last one?
50%.
Why 50%?
Because you have an S and a P, it should be equal amounts.
I have equal amounts of S and P, 50%. What happens to the next one?
33%.
33%. First one,
25.
25%. So this is our S character. Why is this important? Well, where's the S orbital?
So lower energies.
Lower energy in comparison to the hydrogen or p orbital. What's its distance from the nucleus? Much closer to, well, much relatively, closer to the nucleus. Why is that important? If I look at this bond, what's going to happen to the electrons? And an sp going all the way up to an sp3. Careful. At 50% S, our electrons are actually closer to the nucleus, so that actually puts them at slightly lower energy. Let's evaluate that a little bit closer. We're saying that in an sp hybridized carbon, it holds its electrons, or has its electrons, closer to it than an sp3. I wonder if we had some kind of way to represent the ability for an atom to hold electrons, in particular, electrons found in a bond. Electronegativity. Oh, we do have a way. What happens? Electronegativity is that chi sound symbol. As we become less hybridized, we become more electronegative. Why is that important? Well, if we evaluate the bonds and say an alkane, we said those are all nonpolar covalent bonds. Right? Minimal reactivity. Right? So virtually nothing. So when we look at alkanes, it's like it's nothing. There's really not a lot we can do. But when we slowly move our way up or down in our hybridization and we get to an alkyne, that carbon has become much more electronegative. So much more electronegative that what does it do to the electrons holding the hydrogen there? Takes them away. Well, if there's now no more electrons holding on to that hydrogen, what do we have? Okay, we pushed it to the extreme. We said there are no electrons holding that hydrogen there. Push to an ion, we've got a negative carbon and positive hydrogen. Where have you seen positive hydrogens before?
Acids.
Acids. By changing the hybridization, we took a structure that had no reactivity, and it now actually has acid-base chemistry. All based off of a hybridization change. Right? Pretty impressive. Still not that acidic, but we can make it relatively reactive. So our hybridization theory gives us something about electronegativity, and it gives us something about bond rotations. Both of those are going to be exceptionally important. So when we go through and label things, you'll hear me refer to, and I tried to avoid referring to it earlier this semester, as sigma and pi bonds. Okay, your sigma bonds are your single bonds. Okay, we don't care about rotation because they will freely rotate. Well, I guess we do care about rotation because they do freely rotate. Pi bonds are your multiple bonds, double bonds or triple bonds. Okay? There we cannot rotate. Okay? So we can actually kind of eliminate our thought process about thinking about rotation because it doesn't happen. Okay? So if you see a pi bond, no rotation. The next thing that we can look at as we increase hybridization, oh, good, I did that right. We have more orbitals involved, and in particular more p orbitals. P orbitals are higher in energy. Okay, so as we increase hybridization, we move to higher energy states, or higher energy electrons, and we get less electronegative as we involve more orbitals. Okay? So those are some pretty big conclusions that come out of this chapter. Okay, the bond rotation we will use almost instantly in Chapter 4. But before we move into Chapter 4, we get the oh-so-fun section of nomenclature. Okay. So we will come back to molecular orbital theory later, and I'll deal with that later, but I want to look at nomenclature and kind of get through some of this. Okay, anybody recognize this? We got Romeo and Juliet. What's in a name? That which we call a rose by another name would smell as sweet. Okay, why do I find this particularly relevant? Okay. You can not know my name the entire semester, but you can still get through this class not knowing that information. You can not know how to name pretty much every compound that we talk about this semester, and you could still be an exceptional organic chemist. I don't really care that you know how to name something, okay? Because it's a question of, did you memorize that particular rule? What I care about is how it reacts. Okay? What can you do with that structure? That's why we spend a lot of time drawing Lewis structures and looking at these charge distributions and hybridization theory. That said, nomenclature is an important topic, and there's lots of old, primarily male, very nice people, because I'm recording, that insist on nomenclature being this big aspect that everybody needs to know and understand. Okay? Yes, it is important to talk about nomenclature and have some understanding of what's going on with it. Okay? But it's just a rule. So if you look at your textbook, you're going to see all these examples, and they'll throw tons of problems at you. And all it is did you know the rule on how to name this compound? Okay? So you have to know those rules, and that's pretty much it. Okay? This slide right here is what I constantly reference. There's a ton of information on this slide. When it comes to nomenclature, this is what I look at when I try, or what I actually have memorized when it comes to nomenclature. There are some basic pieces that you need to know. These are those basic pieces. There's lots of other rules. Okay? All of that comes from practice and working with it. To give you an idea of my opinion of nomenclature, on where it kind of stands, if you didn't get the idea already. First time taking organic chemistry, I dropped out of it because I was failing. Second time, I changed my perspective on how I went into it and evaluated the course. I said, okay, nomenclature, they talk about it a lot. So, well, do I need to understand it? So I looked at how many questions showed up on the homework and on the exams. It's about 10%. I don't need it. Anytime it showed up, I ignored it. Showed up on the exams, left it blank. Okay? Just moved on. Okay? That's how little of importance it really is. Okay? That said, what was my grade the second time around? About an 89.5%. Okay, which meant if I had done any of the nomenclature, I could have had an A. Okay? So with that in mind, when I ask questions about nomenclature, I do expect you to work them and practice them, but a lot of it is going to be on your own time. I'll set you up with some of the basics and the fundamentals behind it, and you can ask questions about it, but everything I've got has only been picked up from just people asking me questions. I hate reading stupid rules, and that is all nomenclature is. To push this a little bit further, how many of you have taken biology? A lot of people have taken biology. Have you heard of the nomenclature system in biology? Oh, that's interesting. Nobody raises their hands. That's because there isn't one. Okay? As much as I hate nomenclature, it has a very useful and valuable purpose. Because if you shift into the nomenclature system that biology has picked up or that biochemistry has, they just make stuff up because they feel like making stuff up. There is a rule set when it comes to organic chemistry. A bunch of probably old white men sat down and said, this is how you name it. What happens if you can draw the structure, but you use the wrong name? Get to the exact same structure. You're wrong. Okay? You must follow their rules. Okay? Some really quick basics. Just want to jump through to the part that I think is the most relevant. We'll come back and look at these. Is looking at what's in a name. So there's a lot of information stored within it. I tried to color code this so you can kind of pick up those pieces. So you get a location of where groups are located. Right? You get an amount of a particular group, which we'll refer to as a substituent. Then you get the name of the substituent. Then you get the number of, or you keep doing that until you've named all of the individual pieces that come off of it. Then you get the name for the number of carbons, because calling a structure forane just sounds weird. Okay, so we came up with a name for 4. That's our bute. Okay? Then you get your carbon hybridization. Is it sp3? Is it sp2? Is it sp? Ane, ene, ine. Okay? Those are your endings for those hybridizations. And then you can get the location number followed by the functional group, okay, if you hadn't already specified it. Okay? These problems have been color-coded to match that coloring. There is something in the quotes. What is that? Oh, shape. Okay. Shape sometimes potentially shows up. Okay, so we will go through and work these examples, or some of these examples, on Wednesday, and then we will jump straight into Chapter 4. We will definitely cover Newman projections before the exam. We will probably not